Hi, I'm Robert, and today I'm going to talk about our problem scenario from the subject of analysis of signals and systems. And well, we were asked to provide a working MATLAB program of our proposed analysis of the voice signal that identifies one voice signal in particular from others, explaining limitations of our solution. Well, in order to do this, we created this MATLAB code that what it does is that it takes some inputs, the first one being the number of seconds you want every recording to take, the number of persons that you want to record, and the number of recordings per person that you're going to have. By default, they are 5. Then you gotta provide a phrase that every person is going to read. If you don't provide one, the default one is, este es el reto de la materia de señales y sistema. After that, well, the program will record the number of recordings you asked for it, and it will storage them. And with that, we can do some statistics. Well, in order to address the challenge, the code in MATLAB that we developed has these different properties. We have the recording. We have, well, the recordings are captured at 16 kilohertz at a 16-bit mono, and the audio files are saved in the project, including the metadata of each one, and the recordings are analyzed with waveform, spectrum, PSD, autocorrelation, and histograms, among others, including some statistic results. And well, the program will compute the frequency domain representation of the voice using FFT and PSD, with the FFT showing the raw frequency content, while the PSD shows the frequency distribution. Finally, a 1NN classifier performs a leave one out test, generating accuracy metrics. Well, as we talked earlier, so these were the graphics that we got from the program. The first one being this one, that is the plot between voice and frequency, and it shows the plot between the distribution of the voice per frequencies. It shows us the most common frequencies that are on the recording. And well, there are a lot. The second one is the signal amplitude variation over time. It basically shows that in the first seconds of the duration of the recording, the user spoke in the first 0.3 to maybe 0.8 seconds for a half a second. We have some other statistics here. This one, for example, gives us the frequency content of the autocorrelation in terms of power, with the peaks, these peaks corresponding to dominant frequencies in the speech, like the pitch and harmonics, while reducing noise influence. We also have this one describes the waveform for speaker 1 across all the recordings, which in this case we took 3 recordings, so well, it is also normalized in order to emphasize the main duration instead of the loudness of the recordings. Well, finally, we simulated a phone recording. Here it is the graph that we took. And well, basically this plot told us that the telephone channel simulation revealed significant spectral alterations compared to the original high quality recordings, as we can see here. And we can also see the PSD original versus the phone one. And here we can see that the original signal maintained spectral content up to 8 kilohertz, while the telephone simulation eliminated frequencies below 300 hertz and above 3,400 hertz, preserving only the core forming region. Well, thank you.